Hello all. In this video, we are going to see the solution for the GATE 2022 Aerospace Engineering, a topic related to aerodynamics that includes fluid mechanics, aerodynamics as well as gas dynamics as well. So all the questions that are related to these three topics which comes under aerodynamics will be solved in this video. With no further delay, let's get into the solution of the questions which has been asked in the GATE. Let's start with the first question. The point of maximum entropy on a Fano curve in a entropy temperature diagram, which is TS diagram, is. So they given multiple option. What they're basically asking is, at the point of maximum entropy, what is the condition will happen? So for that, we need to understand this graph. If you see here, right? So this is the TS diagram or HS diagram of the Fano flow, where if it starts from a supersonic flow, it will decelerate, the friction will decelerate, and by the time it reaches to the maximum entropy, it will attain the sonic Mach number. If it starts from subsonic flow from here, it will accelerate, and by the time it reaches the maximum Mach number, that's the point it will get the maximum entropy. So at the point of maximum entropy, your Mach number will be 1. So basically the sonic condition Mach number will be reached. So that way, if you see, the option C is the right answer. At the maximum entropy, the flow will reach the sonic Mach number, irrespective of whether it is a supersonic flow or a subsonic flow. Okay, and consider a two-dimensional potential flow over a cylinder. If the free stream speed is u infinity, the maximum speed on the cylinder surfaces So this is a very straightforward question. So on the surface of the cylinder, you know that it's coming from the potential flow theory. On the surface of the cylinder, we know that the radial velocity will be 0 on the surface of the cylinder. So if the cylinder is like this, if the flow is going like this, on the surface of the cylinder, radial velocity will be 0. Only the theta direction velocity will be there, and the formula for theta direction velocity is minus 2 u infinity sine theta, right? And the maximum value of sine theta is 1, right? The maximum value of sine theta is 1. What is being asked? The maximum speed on the surface of the cylinder. So the maximum value of sine theta can become 1 only. So if you substitute that, maybe at this point as well as at this point, right? So your v infinity will become minus 2 u infinity. If you just take the magnitude, the maximum speed it can reach on the surface of the cylinder is 2 u infinity, which means that double the time of the free stream velocity. So option C is the right answer. Yes. Coming to this question, consider a two-dimensional incompressible flow over a non-porous flat plate as shown in figure. For the control volume PQRS, so here the control volume is PQRS. So this entire rectangle like shape is the control volume. So PQRS, okay. And what is they are telling is, for the control volume, the speed u infinity is at section PQ, right? At section PQ, the speed is u infinity, right? And at section RS, they have given the variation of speed, right? They have given the variation of speed, which means that because of this flat plate, there is a velocity profile is getting, because of the shear stress and all those things. At the wall, the velocity is 0, and the velocity profile is given to be u of y is equal to a naught into y by h whole power n, where n is a positive integer. So it could be 1, 2, 3, any number. We don't know that. That's fine. So they're asking the value of A naught for which the flow through the section PS will vanish. So flow through the section PS is which is perpendicular to the plane, right? I mean, you can clearly see that, right? So that will become vanish. If you assume that there is no flow through the section PS, then what is the value of this constant A naught? So again, this is a straightforward problem. How to solve this problem is we have to apply the continuity equation or the mass conservation equation, and you have to use the fact that there is no flow across section PS. That's the only fact that you need to use. So keeping that in mind, it is very simple. Let's substitute the conservation equation, then we will be able to get the answer. So let's start with mass conservation. So which is basically the continuity equation. M dot PQ, which is the mass that is coming in, right? So M dot PQ is the mass that is coming in. That should be equal to the mass that is going out, right? So equal to M dot PS, which is the vanished flow that has been given in the question, plus M dot RS. So M dot PS is this one, this surface, right? But they have clearly told the flow through that PS section will vanish. And M dot RS also we have put. But since the flow through the section PS is vanished, we can consider this mass flow rate to be 0. So now M dot PQ equal to M dot RS. So M dot PQ is nothing but rho A V is equal to, because here V is kind of constant, right, which is U infinity, which is given in the question. At the section it is kind of U infinity, which is constant, whereas in the other hand it is not constant, right, because velocity is a function of y. So how we can put that is integral 0 to h, because the plate h is distance is 0 to h, and let's substitute the velocity variation that is given in the question. A naught into y by h the whole power n, right? So this is the velocity variation into b into dy, where b is nothing but you can consider the width of the plate. Okay, so if the plate is like this, right, so the plate is given like this and this distance is h, b is nothing but the width of the plate which is perpendicular to the screen. Okay, that's how it is. So now if you equate this to the right hand side, what is there in the left hand side? Rho, and here also there is one more row will also be inside, and area is nothing but h into b, right, because we have considered the width to be b. You can either take to be b or you can consider to be 1 also, that's also fine. Rho into h into b into u infinity, right? V is nothing but u infinity. Now if you equate this, you can b and rho can be taken out of integral, and a naught is also again a constant, you can take that out of the integral as well. Y by h the whole power n into dy, that's it. So now rho b will get cancels each other, so you will be, then now you have to do the simple integration. So how will you do that is u infinity h is equal to a naught. If you integrate y by h the whole power n into dy, then you will get y power n plus 1 divided by h power n from 0 to h. So here also limit you have to put 0 to h. So u infinity h is equal to a naught, and if you substitute the limits, h power n plus 1 divided by h power n, and then a naught is equal to u infinity into h power n into h power n into h divided by h power n plus 1. In the integral, we also missed out on one thing, right? So there will be h power n plus 1 divided by n plus 1, right? Yes. So that n plus 1 will be coming here. So now if you cancel each other, h power n plus 1 and this entire time will go out, right? H power n into h will become h. So your a naught will become finally u infinity into n plus 1 will be the answer. So just that you have to do the mass conservation and finally you'll get the answer to be a naught is equal to u infinity to n plus 1. I think the option is B. Yes. Moving ahead to the next problem. Yeah, this is a very conceptual problem. So you need to just understand the concept of viscous force. So viscous force is nothing but, so first let me read out the question. Consider the velocity distribution. So they have shown the velocity distribution in such a way. So as the y-axis is getting increased, the velocity is getting decreased. For the two adjacent layers, L1 and L2. So this is layer 1, this is layer 2. The viscous force exerted by L1 on L2. So every layer will exert some force on the neighboring layer. Now they're asking the viscous force exerted by layer L1 on L2 is in to the right or the left. They have talked about the direction. So viscous force is nothing but the force that has been applied. For example, if a lot of fluid particles are moving in one layer, if this is one layer and the other, if the flow direction is this direction, okay, either very close to the next layer, the fluid particles are moving like this. What does it mean is the force that has been extracted by the top layer to the bottom layer or the adjacent layer in the opposite direction of the flow. So that's the reason you see near the wall, you see the viscous flows will be very, very higher. The force will be very high. So that's why you don't get any flow here, right? Ultimately at this point, the velocity is zero. So slightly, so as you move away from the wall, the effect of viscosity will come down or the force will. So basically viscous force is nothing but it's kind of a drag force, right? It's kind of a drag force. So drag force will always act opposite to the direction of the flow. If the flow is going in this direction, then the drag force will act in the opposite direction. Similarly, in this case, the flow is flowing like this, right? The flow is flowing in this direction. So the viscous force will act in the opposite direction, right? So the layer L1 will put the viscous force on the layer L2 in the opposite direction. That's the reason you see the total velocity is getting decreased, right? It is supposed to, the total velocity is supposed to be like this, right? If there is no viscous effect, the every velocity will be equally like this, right? But that's not happening because every layer is putting some resistance to flow. So viscous force will act in the opposite direction, so which is to the left, because the flow is going towards the right, so the viscous force will act towards the left. Okay, good. Okay, next question. Yes, across an oblique shock wave in a calorifically perfect gas. That's very, very important. So first let me tell what is calorifically perfect gas. So you all know perfect gas is nothing but it has to follow the ideal gas equation, so which is nothing but P is equal to rho RT. Calorifically perfect gas is nothing but where it is Cp and Cv are constant. So those gases are called calorifically perfect gases. So across an oblique shock wave in a calorifically perfect gas, what are the four options? Option A, B, C, D. The stagnation enthalpy changes. So basically flow across a shock wave is an adiabatic process, right? We all know that if this is the oblique shock, the flow across the shock wave, so if for this is the verge and this is the oblique shock, for example, the flow across the shock is an adiabatic process. So in an adiabatic process, your total temperature remains constant, right? So which means that your T01 is equal to T02. Since H0 is nothing but Cp into T0, right? So since it's a calorifically perfect gas, Cp will also be constant. So your H0 will also be constant for a calorifically perfect gas. Hence, the stagnation temperature will also not change. The stagnation enthalpy will also not change. Stagnation entropy will definitely change, right? As we all know, the formula for stagnation entropy is what? The ratio of total pressure right? P naught 2 divided by P naught 1 is equal to e to the power minus of S naught 2 minus S naught 1 divided by R. So this is the S naught 2 minus S naught 1 is the entropy, stagnation entropy change. Stagnation entropy change is definitely a function of the pressure change across the shock. Across the flow, the stagnation pressure will definitely change because that's the flow loss, right? That we all know. So because of that, statement B is correct. The stagnation entropy changes. Then option D is the speed of sound also changes because what is the equation of speed of sound? A is equal to root of gamma R T. Temperature, see, the total temperature only remains constant, but the static temperature will be different, right? T1 and T2 will be different. T1 will not be equal to T2, right? So speed of sound A1 is equal to gamma R T1, A2 is equal to gamma R T2. So definitely the speed of sound in the medium before the shock and the after the shock will be different because of its static temperature change. So option D is also right. So it's a multiple select question. So B and D, both of them are correct, right? Let's move on to the next question. Yes. So this question is very straightforward. You have to just know the knock-on nomenclature. So it's a 4-digit aerofoil. NACA 2412 aerofoil has. So for this, I just given the each digit significance here. So the first digit will describe the maximum camper as percentage of chord, and the second digit will describe the distance of the maximum camper, where that maximum camper is occurring with respect to the percentage of 10% of the chord. The last two digit will give you the thickness of the percentage of the chord. So in that way, if you go, so 2% is the maximum camper with respect to chord, right? Because the first digit represents the maximum camper, but it is given 4%. So this is not correct. Maximum camper is at 40%. That's right, right? The second digit is nothing but the 10% of that second digit is nothing but that's the location the maximum camber will happen. So option B is right. So then C is like 12% of maximum thickness to chord ratio. That's also right because the last 2% will tell you the thickness of the maximum thickness of the airfoil, right, to the chord. So 12%, that's also right. D is like maximum camper occurred at 20%. So maximum camper occurs as 40% because the second digit only. So D is also not right. So B and C are right. So you can refer to these statements. This will help you to give the answer. So this is a very straightforward question. Okay. Yeah. So this is an interesting question. A cylindrical object of diameter 90 millimeter is designed to move axially, which means that if this is the cylinder, for example, if this is cylinder object, the cylindrical object is moving axially. So which you can imagine that the cylindrical object is like this and the flow is coming and hitting like this. Okay, so that's what it is. Its drag is estimated on a geometrically half-scaled model in water. See, the cylindrical object is moving in air. Keep that in mind. The cylindrical object is moving in air, but the geometrically scaled object is moving in water. So all this estimation has happened in water. So there is a basic difference between the mediums. Okay. Okay. Assuming flow similarity. So now they have given, so they have clearly given between the prototype. The prototype is the cylindrical object and the scaled, geometrically scaled object is moved in the water. And the prototype and the scaled object is having a flow similarity. So as soon as they say flow similarity, then we can say that Reynolds number of the prototype will be equal to Reynolds number of the model, right? So that's what flow similarity means. We can equate the flow Reynolds numbers. Now they are given coefficients of dynamic viscosity and density of both air and water has been given. Well and good. And now they're asking the drag measured for the model. When the model is moved in the water, right, the half scale model, the drag is given, which is 2280 Newton. So drag of the model is equal to 2280 Newton, which is given in the question. Now they're asking what is the drag experienced by the cylindrical object, the actual prototype. So for that, actually, what is the formula for drag? So the formula for drag is So drag of the prototype is equal to of rho Vp square, velocity of the prototype, Vp square into S, the surface area, into CD, right? That's what it is. What is the drag of the model? It's just the same. So drag of the model value is given to us, which is equal to 2280. So here I can write 2280 Newton, which is equal to of. So here drag of prototype is density air, okay, because the prototype is moving in air. But here it is density water because the model is moving in water into V model velocity square, right? Into S model. So here S prototype, surface area prototype into CD. The CD will be same, right? Because it is it's a similar, there is a flow similarity that has been existing, right? So what we are going to do now is we are going to calculate the CD using this drag model. Then we are going to substitute it here because we know the velocity at which the cylindrical object, which is the prototype, is moving. So Vp we know 60, which is given in the question. SP we know because 900 mm is question given in the question. SM also we know, the wetted surface of the model also we know because it is geometrically off scale. Through that we can calculate. The only thing which is unknown to calculate CD of the model, which is the same as the CD of the prototype, is nothing but velocity. Vm we don't know. So to calculate Vm, we are going to use the flow similarity, which is nothing but the Reynolds number of the prototype and the model will be equal. So let's do that calculation. The Reynolds number of the prototype and the model will be equal. So Re prototype is equal to Re model. So what is the Reynolds number formula? Rho air into diameter of the model into velocity of the model divided by mu of water, right? Sorry, mu of air, sorry, these are all prototypes, I'm sorry about it. Rho air into diameter of prototype, velocity of prototype divided by mu into air, which is equal to rho water, diameter of model, velocity of model divided by mu water. Now we know everything in this equation except Vm. Velocity of the model we don't know, but prototype is given in the question. So V air is given, see, rho air is given to be what, 1.2. dP we can just keep it at dP only, no issues. If you want, you can substitute 900, otherwise we can keep it dP for the simplicity of mathematics. Vp is given to be 60 meter per second and mu a is nothing but 1.86 into 10 to the power minus 5, which is given in the question, right? You see here, yes. Similarly, rho w is 1000. dm is nothing but dp by 2, right? Because it is half scaled model. You see here, half scaled model. So if it is 900 millimeter, then the half scaled model is 450 mm. That's why I just kept this to be dp, and here I am substituting in dp by vm. We don't know, that's what we are calculating, into mu. Mu is nothing but 1.01 into 10 to the power 3 minus 3. Now in this equation, I think everything will get cancels each other. Finally, we can calculate Vm, and the Vm will come out to be 7.82 meter per second. So now we have got Vm. Now let's use the drag equation of the model. So dm is equal to of rho water. So basically this equation, okay, into Vm square into Sm into CD. So which is equal to, drag of the model is given 2280 of into rho w water is 1000 into Vm square we just calculated is 7.82 meter square whole square into Sm. We have to be slightly careful here because it's the projected area, right? See, this area this entire area, right? This entire area. So this is nothing but the area of the circle, right? Is getting seen by the fluid, either it is water or air, right? So if you take the circle area, it is pi d square by 4, right? If you reduce the scale by half the time, then this will become, if this is the area of, if this is equal to the area of the prototype, then area of the model will become d by 2, right? So essentially it is pi d square by 8 it will become, sorry, 16 it will become, because there is one more 4, right? D by 2 the whole square will become, what will happen? There is already a 4, into 4 it will become. So basically, if you rewrite this, SM will be equal to SP by 4, where SM is nothing but wetted area, surface area of the model, is equal to SP by 4. You have to put, you should not put 2 here. Don't think that it is a half scaled model. So the area will be half of the prototype. Since it is a cylinder, the area will be, if the model is diameter is reduced by half, but the area will get dropped by 4 times. Okay, so keep that in mind. So now instead of SM, you can put SP by 4 into CD, right? So now in this equation, everything is known except CD. Yes, SP we'll just keep it as SP only, so that it will be easy for us to cancel. Then CD will become something like this. Okay. So if you cancel everything, what will happen? So this will become 500, and this 4 will be there, 7.82 the whole square, and all those things. If you do all those things, finally you'll get the value of the CD. Now you go and substitute the value of CD in the dP, because that's what is asked in the question, right? dP. So what is dP? dP is equal to half, rho is 1.2, V square is already given in the question, 60 square, into SP. SP is the surface area of the prototype, into CD. Instead of CD, the value that you get here, right? SP by 4 and all, it will come something like this. Okay, 0.15 by 2 SP it will come something like this. Okay, 0.15 like this, into 2, not by 2, into 2. So basically, and if you substitute this back here, right, I think then it is 0.30, right? So 0.30 into divided by SP. So all these things will get cancelled. Finally, you'll get a dP to be 664 Newton, which is option B. The only thing you have to be careful here is when you replace your area, don't just think that it is a half scale model. So my area will be half of the time of the prototype. No, area will be reduced by 1 by 4th, not 1 by 2, because it is pi d square by 4 is the area of the cylinder. And if you reduce your diameter d by 2, then whole square will become, so it will become 4 times. That's where you have to be careful. So it is 664, sorry, 644, sorry, 644 it will come Newton. If you substitute this, you'll get that. Okay. Yes. The next question is, the rotational velocity field in an airflow is given by the velocity vector axi vector plus bxj vector, where a and b values are given. So basically, if I rewrite this velocity vector, I can write like this. V vector is equal to 10 yi vector plus 20 xj vector, and then the small u is nothing but 10y and the small v, velocity along the y direction, will be 20x. That's what is given in the question. They are given the air density and the pressure at x and y is equal to, so they are given pressure at x and y is equal to 100 kilopascal. So pressure at 0, 0 is 100 kilopascal. That is also given in the question. Neglecting the gravity effect, the pressure at a point 6, 8. Okay. So this is a kind of problem which is given, like the general velocity field is given, right? The velocity field is not given with respect to a particular streamline or not. So here you have to use the Euler equation because you get the velocity for the field, right? Not for a particular streamline, and it is also clearly given rotational velocity field. So even if it is irrotational flow, then Bernoulli's equation can be applied even across the streamline. But that's where it is clearly given that rotational velocity field. So it's a field. The velocity vector is given for a field. Similarly, you derive a pressure form for the given field using this velocity vector. Once you get the pressure for the given field as a function of x and y, then you substitute the value of your x and y, then the pressure value will get it. So for this we have to use Euler equation, which is the differential form of Bernoulli's equation, right? So basically if you integrate Euler's equation, you'll get Bernoulli's equation, but in this case you have to use Euler equation only because it's a field problem. It's a field problem, right? Because the generalized velocity vector for the entire field is given. So we all know, right, what is the Euler's equation, right? So Euler's equation is very simple. 1 by rho grad p, which is divergence of p, is equal to d b vector by dt. So this can be easily written as acceleration vector, right? Minus negative sign will come, sorry about it. 1 by rho del p is equal to minus dv vector by dt, so which is nothing but your acceleration. So this is vector, so how will you get 1 by rho del p is equal to minus of ax I vector plus ay j vector, and you'll also get a z k vector, but since it's a two-dimensional problem, I'm neglecting that, right? So now if you expand this, right, what is gradient dou by dou x I vector plus dou by dou y j vector, right? So what will become 1 by rho into dou p by dou x I vector plus dou p by dou y j vector is equal to minus ax I vector minus ay j vector. So you have to basically match these. So dou p by dou x is equal to minus ax. So like that you have to get. So from this equation, you can equate all the ith term, all the jth term. So what will happen in that way? 1 by rho dou p by dou x is equal to minus ax, which is nothing but acceleration along the x direction. Similarly, 1 by rho dou p by dou y, which is equal to minus ay. So now you have to find what is this acceleration along x direction, acceleration along y direction, and substitute it here. Then you integrate, then you will get the p as a function of your x and y, p as a function of your flow field. Then you substitute the value of x and y at that function, you'll get the pressure. So for that, we all know, right, what is ax, right? Ax is nothing but since it's an steady flow, we will ignore the unsteady term. So we'll get only the convective acceleration, u into dou u by dou x plus v into dou u by dou y. Again, w will come into picture. Since it's a two-dimensional problem, I'm just stopping here only. Otherwise, you will also get w into dou u by dou z will come. But now, as of now, it's a two-dimensional problem, so I'm neglecting that. Similarly, what is ay? Ay is equal to u into dou v by dou x plus v into dou v by dou x and dou v by dou y. So now let's find out this. So I have already mentioned what is u and what is v, right? U is 10y, v is 20x. So in this case, dou u by dou x will become 0, right? Because there is no u term. So this term will go out. V into dou u by what is v? 20x. So 20x into what is dou u by dou y? Dou u is 10y. So dou u by dou y is 10. So 20x into 10, I think it will come out to be 200x. Ax equal to 200x. Similarly here, dou v by this term will go for 0, right? Because in the v term there is no y involvement. So this term will go for 0. Whereas dou v u is what? 10y. Dou v by dou x is 20. So again this is 10y into 20. So which is nothing but again 200y is the acceleration along the y direction. So now let's equate this here. 1 by rho dou p by dou x is equal to minus ax. What is ax? 200x. So it will become minus 200x. Similarly, 1 by rho dou p by dou y is equal to minus ay. Ay is what? 200y. So minus 200y. So now let's integrate this to get p. P is equal to minus 200 x square by 2. Similarly, if you integrate this equation, you will get p is equal to minus 200 y square by 2, right? Plus c, you will also get a constant. So if you add these two things, right? So you'll get the entire p to be p is equal to 200. There will be one row here, right? That row will come here, okay? Because it is in the denominator here. That row will come here. So 200 rho, if you take one of the minus sign outside, x square plus y square by 2 plus c. C is nothing but the constant of integration, right? If you integrate it, you have to sum these two things, right? So now to find out the c, they have given some condition. P of 0 comma 0 is equal to 100. That's what they have given. So if you substitute that in this equation, x square is equal to 0, then this term will become 0, then which will implies that 100 is equal to minus 200 rho 0 comma 0, this will become 0 plus c. So this will implies your c is equal to 100, your constant. So you got the term, your p is equal to minus 200 rho into x square plus y square by 2 plus 100, right? So this is the pressure function of that flow field. How they have given the velocity function of the flow field. So this was the velocity function of the flow field, right? Now using this velocity function of the flow field, using the Euler's equation, because it's a field function, right? It is not along a streamline. They have never mentioned anything like that. So we use the differential form of the momentum equation, which is Euler's equation. We got the pressure as a function of x and y. Now what is the question that is asked is pressure at x is equal to 6 and y is equal to 8, right? Yes, pressure at x is equal to 6 and y is equal to 8. So if you substitute that, minus 200, rho is given to be 1.2 or 1. 1. Yes, the air density is given to be 1. So you can substitute this to be 1 into 6 square is 36 plus 8 square is 64 and divided by 2 plus 100. And if you solve this, I think this will become 100 then 50. Yes, so something like this, right? 100 and 1. So finally, what will you get? You will get your pressure to be 90, right? 90 kilo Pascal. So the pressure at 6 meter and 8 meter is 90 kilo Pascal. Okay. Okay. And the next question is, yeah. So consider a circulation distribution over a finite wing was given below the equation. So they are given the circulation of the finite wing and it has been given like this, right? So now with that, what they have asked is the wingspan is given to be 10 meter, right? And the maximum circulation, which is the gamma naught, which is given in the question, right, that has been given to be 20 meter square per second. The density of the air is also given. The free stream velocity is also given. Now they are asking the lift over the wing, the entire wing they are asking. So first let me put this like this. If the fuselage of the aircraft is like this, the wings will be like this, right? So this is one wing and this is the other wing. So you can clearly see the entire wingspan will be 10. That's what is given. The wingspan is 10. So that is 10. So this part is 5. This side is 5. Okay. And so this circulation distribution for one side semi span, right? That's why you see 0 to b by 2, then minus b by 2 to 0. So it is like that. Okay. So what I would do in this case is I will calculate the lift over this wing for this semi span, then multiply by 2 because it's a this entire structure will be a symmetrical structure, right? If you cut the fuselage off, the shape of the wing in one side and the other side will be the same, and the velocity, everything will be the same. So let's calculate the lift distribution for this semi-span wing, one side of the wing. Then if you multiply by that by 2, then you'll get the lift over the entire wings. So let's do that. So I'm going to take the first circulation distribution, 0 to b by 2, and using that I'm going to calculate the lift. Then finally I'm going to multiply into 2. Either you can do like that, or you can also calculate the circulation of the aerofoil for this second function also, which is from minus b by 2 to, so actually it will work like this, minus b by 2 to 0, then 0 to b by 2, right? So like that it will work. Okay, so that way also you can do, but for the simplicity, ease of mathematics, I'm going to do take this first thing only, calculate the lift over that semi span, and then multiply by 2. That will give me the lift for the entire wing. So using the Kutta-Joukowski theorem, lift is equal to rho u gamma. So here density is given, free stream speed is given 80. Only thing you have to calculate gamma, but gamma is a function of your wingspan. So now let's calculate the net gamma over this semi wingspan or half wingspan, then we'll multiply by 2. For that, let's take this function which is given in the question. So if you want to get the full gamma, right, gamma is equal to integral of 0 to b by 2. See, I'm going to take this first equation, 0 to b by 2, gamma naught into 1 minus, so gamma naught into 1 minus 2y by b. This is the equation into dy. If I integrate it, I'll get the entire equation of lift. And here b is given to be 10, so b by 2 will be 5. So 0 to 5. Gamma naught is given to be 20, if I'm not wrong. Yes, 20. So 20 into 1 minus 2y by b is again 10 here, and into dy. So now if you integrate this equation, right, it is very straightforward. If you integrate, you will get 20y minus 4y square by 2, 0 to 5. Then if you substitute the limits, it will become 100 minus, this will become 1 and this will become 2. I think it's 25, so it will become 50. So the net gamma will be 50 meter square by second. But this is for one side of the wing, because we have taken the semi-span function and did this. So this is the gamma for one semi-span of the wing. So let's calculate the lift for that now. L is equal to, rho is given to be 1.2 into u is 80 into gamma 50. This will give you the lift over one side of the wing. If I want the next side also, I'm just going to multiply by 2. So if I do that, I'll get 9600 Newton. That will be my net lift for this entire wing. Okay. Yes. So let's solve this problem now. This is a typical fluid mechanics problem, right? So it's a very typical fluid mechanics problem. So let's first draft out all the given information of this question. So the height h is given to be 2 meter, okay, which is clearly given, right? And then the delta, which is the thickness, right? This is given to be the gap between the cylinders. So there is a two cylinders, right? So the gap between the cylinders is given to be 5 mm. So delta is equal to 5 mm. That is also clearly given in the question. And they have given the viscosity. So that is also very clearly given. Mu is equal to 10 to the power minus 4 Pascal seconds. So that is also clear. Viscosity of the fluid which is filled, right? That is also clearly given. So now they are asking the inner cylinder is rotating. So the internal cylinder is rotating. You see it is rotating at a constant angular speed. So omega is given. Angular speed of 5 radians per second. That is also good. So now friction at the bottom of the surface can be ignored. Velocity profile in the vertical can be assumed to be linear. That is very much important. So they are given the velocity profile inside is linear. You can assume it to be linear. Velocity profile in the vertical gap between the cylinders can be assumed to be linear. The driving moment required for the rotating motion of the inner cylinder is. So basically they are asking this torque, right? That's what is the driving moment, right? So that is very, very straightforward because the torque applied is equal to will be equal to torque because of viscous. Okay, so keeping this in mind, so now torque viscous is equal to viscous force into radius. So how do you calculate viscous force? So viscous force is nothing but shear stress, which is viscous stress, tau viscous into area, because stress into area will give you force into radius, so that you will get the T viscous. So how do you calculate tau? From Newton's law of viscosity, we know that tau is equal to mu into dou u by dou y into area into radius. So now nu is given in the question. Now what you need to get, how do you get dou u by dou y? For that they have clearly given it's a linear velocity profile. So you can use this, right? So basically r into omega, that will give you the linear velocity, right? Right. Minus 0 divided by delta. Delta is nothing but that gap between the two cylinders, right? Into area is nothing but 2 pi r into h, the perimeter area into the total length. So the area is nothing but this entire perimeter area into this length. Okay, so 2 pi r into h into again the radius is there for the torque calculation. So now in this equation we almost know everything, right? Mu into r omega by delta into 2 pi h into r square, right? So in this equation it is very clear that we know everything in this equation. Now let's substitute all these values, which is nothing but what are those values? Yes, so mu is 10 and the radius is given 1. So 10 to the power minus 4, sorry, into radius, inner cylinder radius is given to be 1, omega is given 5, delta is given 5 mm, so into 10 to the power minus 3, into 2 into pi into h is 2, right? Yes, 2 into 1 square, and finally you will get 1.26 Newton meter. So the answer is 1.26 Newton meter. Okay, yes. So now let's get into the next problem. It is very easy problem, though it looks like little difficult. So in a convergent duct area, so they have clearly given it's a converging duct. So the flow is coming like this, and the area is getting decreased. So it's a convergent duct. Velocity at section P. So this is section P. Here the velocity is 1 meter per second. So velocity is equal to 1 meter per second. 15 meter per second. Sorry, velocity is equal to 15 meter per second, and the pressure is area is 1 meter square. Sorry. In Q, section Q, they are telling they have not given any information about the section Q, but what they wanted to ensure is the flow needs to be incompressible for them. So which they have given a guidelines. If the Mach number is less than 0.3, then the flow is incompressible. So to ensure that the flow should not exceed the Mach number more than 0.3, what should be the minimum area that is required at section Q, so that the flow will not be more than 0.3 Mach, so that it still remains incompressible. So they want the flow to be incompressible. So that's the whole idea here. Okay, so we can take like this. At this section, m is equal to 0.3. That's the condition. And one more information is given. The fluid is temperature is given, which is T is equal to 300 Kelvin, and it is clearly given it's an isothermal process. You can assume the flow to be inviscous and isothermal, which means that temperature is not changing, because temperature at P is also 300. The temperature at Q is also 300. Okay, now let's use our content equation. Rho1 A1 V1 is equal to Rho2 A2 V2. Since they wanted the flow to be remain incompressible, I consider that there won't be any density change. So A1 V1 is equal to A2 V2. So now A1 and V1 are given, nothing but at section P. So basically if I rewrite this, AP VP at section P is equal to AQ VQ, right? So AP and VP are given. So what is A1? What is VP? 15. We have to find this AQ. Good. But we don't know what is VQ. Instead of VQ, we have to find VQ, but some informations are given to us. They have told that the Mach number should not exceed 0.3. Then what is the minimum area required? So relationship between Mach number and velocity is V by A. Right? From here, if you want to calculate VQ, VQ is equal to MQ by speed of sound A. Speed of sound will not vary because they have clearly told it's an isothermal process. So with that, let me put VQ here. Mach number at Q is equal to velocity at Q divided by speed of sound. So now velocity at Q is nothing but 0.3 is the Mach number into speed of sound is root of gamma RT, and that can be written as, all the values are given, right? Yes, gamma is 1.4, R is 287. So 1.4 into 287 into temperature is 300. The root is there everywhere, okay? If you calculate that, you will get your VQ to be 0.3 into, you can put this rest of the value. I have not calculated it, I directly substituted that in the equation. So now go back to the equation. It is 15, the left hand side is 15, which is equal to AQ. Instead of VQ, you substitute this value 0.3 root of 1.4 into 287 into 300. Now the only unknown in this equation is AQ. If you find that the minimum area, at least the area has to be this much, which is nothing but 0.144 meter square. So at least the area has to be 0.144 meter square so that the, the Mach number will not exceed 0.3. If the area is greater than, if the area is greater than 0.144, that's fine, well and good. Okay, for example, instead of 1.144, it is 0.2. Still, the Mach number will be less than 3. But if it goes below 0.144, then the Mach number will be more than 0.3. Then they cannot maintain the incompressibility. Okay, so that's the reason. So minimum area required at section Q is 0.144. Okay, so this question is very straightforward. You don't need to worry too much. It's a very straightforward question. And they have given that the angle of attack of a symmetrical airfoil. So basically alpha is given 2 degrees and velocity is given, V infinity is given to 50 meter per second. Now they are asking the pitching moment coefficient about the leading edge rounded off to 3 decimal places. So CMLE is equal to minus CL by 4. That's the formula. Instead of CL, they have given alpha. So the relation between CL and alpha is equal to, CL is equal to 2 pi alpha from thin airfoil theory divided by 4. Minus will be there. So here if you substitute instead of 2 pi, but 2 pi is in radians, right? 2 pi is per radians, the slope, lift curve slope, right? 2 pi is in per radians. Alpha is given in degrees. Either you have to convert alpha to radians, then you can, this 2 degrees to radians, then you can substitute 2 pi into that value, or you need to convert this per radian slope into per degree slope. So that is a known result, right? Instead of 2 pi per radians, if you convert this into degrees, it will be 0.11 per degree. So that's the lift curve slope into 2 degrees divided by 4. So this will come out to be minus 0.055. So that's the moment about the leading edge, which is minus 0.055. See, I repeat, either if you want to keep 2 pi, keep 2 pi as it is and convert alpha to radians. Instead of this 2 degrees, you convert 2 degrees to radians. Pi by 180 and do that. If not, you convert this lift curve slope, because what is the lift curve slope? Lift curve slope unit is 2 pi per radians. The equivalent of this per radians is nothing but 0.11 per degree. So I'm substituting 0.11 per degrees into, if you get this to per degrees, then you can directly substitute alpha in degrees only, no issues. So which is minus 0.055. So that's the answer. Yes. Moving ahead. Again, this is a very easy question. It looks like little tough, but it's a very easy question. A convergent divergent nozzle with adiabatic walls is designed for an exit Mach number of 2.3. So what they are giving is at the exit, here the Mach number ME is equal to 2.3. It is discharging air to atmosphere, so it is directly discharging the air to the atmosphere under the condition indicated in the figure. So in the figure, the atmospheric air condition is 1 bar, pressure is 1 bar, and temperature is 300 degree at 300 Kelvin. Good. So now the flow through the nozzle is in viscous, right? The flow through the nozzle is in viscous. So the characteristic gas constants are given, which is R is equal to 287, gamma is equal to 1.4. Now they are told the flow is starting from the reservoir pressure of 25 bar and the temperature is equal to 300 Kelvin. Okay, good. If the inlet conditions are like this, the P naught is equal to 25 bar, and if you see this, then the expansion waves are formed here. You know why the expansion waves are formed here? Because the pressure is high here compared to the exit pressure. See, like there is an exit Mach number, like that there will be some exit pressure. why the expansion waves are formed here is the exit pressure is greater than the atmospheric pressure PA. So PA is 1 bar, whereas your PE for this condition of input P naught is equal to 25 bar, PE is greater than PA. Because of that, the nature has to form the expansion waves to decrease the pressure so that when it discharges the air to the atmospheric conditions, it will go smoothly. For example, if the shock waves would have been formed here means then PE is less than PA, then shock waves will be formed to increase the pressure and then the flow will get discharged into the atmosphere. That's how it is. But in this question, it is clearly given expansion so it means that it is kind of under expanded flow, right? It's kind of under expanded flow. So because it is under expanded, uh, it needs further expansions. So because it is supposed to expand more, so it is needs further expansion. So the expansion waves are formed here, and that waves will expand the flow further so that the pressure will be maintained with respect to the atmospheric pressure. So now what is the question asked? The minimum percentage change in the reservoir air pressure required to eliminate the wave system at the noxle. So they don't want this to be, there should be a wave. So basically what they wanted to maintain a PE exit pressure which will be equal to PA atmospheric pressure. If you maintain this, then there is no required of any wave here. Either it is expansion wave or shock wave, nothing is required. So as of now, there is an expansion wave because your PE is greater than PA, right? So that's the reason you need expansion wave to reduce it further. But if you can maintain PE is equal to PA, then you don't need any expansion wave or shock waves like that. So that's why they ask. So to maintain this PE is equal to PA, what is the change that is required at the inlet pressure condition without changing anything else, right? So that was the question that has been asked. So basically, if you see here, right, we have to use flow over a shock is a flow over a nozzle, flow inside the nozzle is an isentropic process. So we are free to use the isentropic relationships. So in that, if you see P naught by P exit. So P naught is not inlet pressure and P naught by P exit. Okay, equal to 1 plus gamma minus 1 by 2 into m exit the whole square whole power gamma by gamma minus 1. Okay, so now if you want your PE to be equal to PA for the same exit Mach number which is 2.3, what is the inlet pressure that is required, so that for the same exit pressure you will get your expansion fan waves get eliminated. So instead of PE you have to substitute PA now. What is PA? PA is equal to 1 bar. So P naught by 1 is equal to 1 plus gamma minus 2 by 2 will be 0.2 into 2.3 the whole square, which is your exit Mach number, the whole power 3.5 gamma by gamma minus 1, which is 3.5. So you'll get your P naught to be 12.504. That's your P naught value, 12.504 bar. This is your new P naught value, so that your exit pressure will be equal to your ambient pressure, so that no expansion waves are required. Then what is the percentage change, minimum percentage change, that is change in the reservoir pressure is required to eliminate the wave system. So if you calculate this, initially the P naught initial is equal to, what is that, 25 bar, right? And the now the new P naught that is required to maintain the to eliminate this pressure system wave system is 12.5. So if you clearly see, it is kind of 50%, right? So we need 50% reduction or 50% change in the stagnation pressure condition so that the wave system can be eliminated. So approximately it is 50%. Okay. Okay. This is slightly a tricky question. A conversion nozzle fed from a constant pressure, constant temperature reservoir is discharging air into the atmosphere at 1 bar. Great. With choked flow at the exit marked as Q. So they have clearly told that the flow has got choked. So first of all, what do you mean by the flow has got choked? So flow has got choked means beyond that you cannot have the maximum unless you change the reservoir conditions. For a given reservoir condition, beyond that you will not have a maximum uh, mass flow rate, which means that, so when you need to consider your flow to be choked, it is your m dot by a will be equal to constant. Okay, that is something like that. M dot a, your mass flow rate per area, right? That will kind of it will be kind of some value. Okay, then you'll consider your flow to be choked. There is no other opportunity for you to increase this m dot a. For that, I will explain it slightly this concept so that it will be easy for you to understand. If this is the like this, right, and it's a converging duct like this, right? Sorry, I did not draw properly. That's okay. Or we can go to the here. Yeah. So it's a converging like duct like this, right? So when the flow will get choked, especially in the convergent nozzle, there is something called exit pressure. Exit pressure is nothing but the pressure at this section, which is PQ. There is something called back pressure. Back pressure, you can consider, in this case, you can consider this to be an atmospheric pressure or whatever it is. Okay, BP. If that exit pressure and this back pressure is equal to P star, which is critical pressure. If this PQ is equal to P star, P star is nothing but critical pressure. I will tell you what is critical pressure. P naught by P star is equal to 1 plus gamma minus 1 by 2. Instead of m square, we'll put 1 square here, which means that it has attained the maximum velocity of maximum Mach number here, basically. So m is equal to 1. So if you substitute in your isentropic relationship, instead of this m, if you substitute 1, what is the value of P star? That is the critical pressure for that given inlet condition, reservoir condition, because your P star is dependent on P naught, right? If you change your inlet condition for a different reservoir condition, then the P star will be different, right? So your P star is mainly, your critical pressure is mainly dependent on your inlet, your reservoir condition of P naught. So for a given P naught, once you say the flow is already choked, which means that the exit pressure, which is PQ, is equal to P star, right? Or your back, which is equal to your back pressure, which is nothing but again. So your back pressure is equal to your critical pressure, hence your PQ, right? Unless you change your reservoir condition, your P star will not be moved. For this given set of input condition, your reservoir condition, which is P naught and T naught, your P star is not going to change unless you change that, your reservoir stagnation conditions. Okay. Once the flow is already choked, right, which means that your PQ is equal to P star. even if you increase your area or decrease your area, not so much things will happen. The flow will, here what I'm assuming here is, since that part of the information is not given in the question, what I'm assuming here is the exit pressure is equal to critical pressure even after the area has got increased. If the exit area of the nozzle is increased while all the reservoir parameters and the ambient condition remains same. So I am taking these things very seriously because the reservoir conditions are same, which is nothing but your P naught and T naught are same, and the ambient condition is also same. Ambient condition is nothing but your exit pressure or something like that. Okay, the pressure at this discharged place are same. Then at steady state, what they are asking. So since your exit pressure is, we don't change anything, because mainly choking, if you see this m dot equation, right, m dot by a is nothing but is a function of root of r by gamma into p naught by t naught into 1 by gamma plus 1 by 2 the whole power gamma plus 1 divided by 2 into gamma 1 minus 1. In this entire equation, this value will get only affected if you change your P naught and T naught. Otherwise, your M dot A will be constant. This M dot A will become constant only when your Mach number at the exit of the conversion nozzle will be equal to 1, which is nothing but your exit pressure is equal to your critical pressure. Unless you change your P naught and T naught, your M dot by A is not going to get changed, but it is clearly given in the question, while all the reservoir parameters and the ambient conditions remain the same. So they are not changing the reservoir parameters, they are not changing your ambient condition, hence your P will also be just the same. So the flow will remain to be choked, right? But if they change the ambient condition and all those things, then the story is different. Okay, the flow will remain to be choked, so the nozzle will remain to be choked. With this, the solution for the GATE 2022 Aerospace Engineering questions related to aerodynamics has been solved. Please let me know your comments, your suggestions in the comment section. Thank you.
If you like this video, please like, share and subscribe my channel to encourage me. Thank you.